Hi, I'm Yingming Gao, a PhD student from Dresden University of Technology. Today, I'd like to introduce our study using tone model for Mandarin Chinese tone modeling and recognition. I will first introduce the background, difficulties, and existing methods. Then I will introduce our proposal and how we validated its feasibility, followed by conclusion and future work. Mandarin Chinese has 4 lexical tones and a neutral tone. Mandarin tone plays a crucial phonemic role so that the same syllable with different tones has different lexical meanings. Therefore, automatic tone recognition is a fundamental research topic which can be used for discriminating homophone words in ASR systems, labeling prosodic information of a database, and detecting tone pronunciation errors of language learning. Figure 1 shows the standard patterns of lexical tones. When pronounced in isolation, their pitch contours seem well-defined and quite stable, resulting in a very high tone recognition accuracy. However, these standard tone patterns seldom occur in continuous speech due to the influences of tonal co-articulation, intonation structure, and the greater contextual variability of neutral tone. The pitch contours of continuous speech usually deviate a lot from their standard patterns. All these tonal variations increase the difficulty of tone modeling and recognition. Traditional methods usually use the prosodic features, such as F0 and energy, as well as their derivatives. Recent methods also employ the spectral features, considering the potential correlation between source features and spectral features. The classifiers used mainly differed in whether or not considering contextual information. Some researchers also tested methods from articulatory point of view, such as using tone nucleus model and phrasing coefficients of Fujisaki model as features for tone recognition. In this work, we tested the use of tone model for tone recognition. Target Approximation Model articulatorily simulated the underlying mechanisms of pitch realization. It assumes one pitch target for each syllable, which is defined as a linear function. The surface F0 is modeled as the system response driven by a pitch target. In figure 2, there are 2 syllables delimited by vertical lines. The dashed lines represent the underlying pitch targets. The thick solid line represents the surface pitch contours that asymptotically approaches these 2 successive pitch targets. Tone model is controlled by 3 parameters: the slope, the offset, and the tau, which controls the strength of target approximation movement. Previous study has found that, for example, the slope has positive and negative values for rising and falling tones respectively. Tau is relatively greater for neutral tones than other tones. There also exists many-to-one mappings between surface F0 and underlying representations. In other words, tone model discovers the relatively less variable underlying pitch targets from the variable surface pitch contours. The derived tone parameters are expected to be distinctive among different tone categories, which was validated with 2 speech corpora. The first dataset consists of disyllabic non-sentence sequences spoken in fixed contexts. It involves only 4 lexical tones. Dataset 2 contains more tonal variations, including tone sui cases and neutral tones. To extract time parameters, we use the Target Optimizer, which is one of the quantitative implementations of a time model. After optimizing hyperparameters, we use it to extract QTA parameters. As listed in Table 1, the mean values of QTA parameters of lexical tones conformed to phonological definitions. For example, the slope characterized the asymptotic direction of pitch contour for each tone. Next, we conducted the multivariate analysis of variance, which showed significant differences of QTA parameters for each tone pair, suggesting the possibility of using them for tone recognition. The same procedure was then applied to dataset 2. Figure 3 shows an example of Target Optimizer modeling pitch contour of a sentence. Although the surface pitch contour of each syllable varies a lot in the beginning part, the end of it gradually approximates its underlying pitch target. Therefore, describing the surface pitch contour with underlying pitch targets might help distinguish tones from each other. We trained 3 SVM-based classifiers contrasted by the input features. The first type is equidistantly sampled 30 F0s, which was taken as the targeted performance system. According to the time model, the transition status from preceding syllable is also required to generate the current syllable pitch contour, and is expected to be helpful to tone recognition. Therefore, the third one further incorporated the onset F0 of each syllable upon the second one. The results showed that the pitch targets conveyed most information for distinguishing tones. With fewer number of features, the QTA parameters achieved comparable accuracy compared to the way of representing pitch contour by 30 F0s. For dataset 2, we also tested a bidirectional RSTM classifier, considering its powerful capability of modeling temporal sequence. Another reason for using it is to deal with carryover and anticipatory effects from neighboring syllables on tonal variation. In addition to QTA parameters, for each syllable, we applied a discrete cosine transform to the original pitch contour, and then selected the first 3 coefficients as the second type of features. We also calculated F0 statistics as the third type of features. As shown in Table 3, the statistical features had the general better performance, especially among the SVM-based classifiers. This may be explained by the fact that they explicitly included information from neighboring syllables. That is, the offset F0 of a preceding tone and the onset F0 of a succeeding tone. The BRSTM-based classifiers outperformed SVM-based ones, indicating its advantages of modeling contextual tonal variation. The long-term memory of BRSTM may deal with the variation due to intonation, while its short-term memory may tackle the variation due to influences of neighboring tones. By incorporating statistical and QTA features, the recognition accuracy further increased, indicating the QTA parameters contain additional information for tone recognition. By discovering the underlying pitch targets from variable surface pitch contours, TAM model can characterize the tone patterns well, and the QTA parameters are distinctive among different tone categories. Besides, BLSTM proved to be more powerful than SVM in modeling tonal temporal dependency. The proposed method was validated on two speech datasets containing human-labeled syllable boundaries. Although the TAM model proved to be non-sensitive to boundaries in previous study, it is still necessary to further verify the proposal using automatically derived segmentation, for example, from phoneme boundary detection. The hyperparameters of Target Optimizer were optimized with regard to root mean square error, which may drive the reproduced pitch contours to overfit the original ones. The corresponding estimated pitch targets might not be the optimal for tone recognition. To optimize hyperparameters using tone recognition accuracy as a metric can perhaps discover more distinctive pitch targets. That's all. Thank you very much for watching my presentation.